Have our speaker today, Cheng from the University of Chicago, and he's been here before, but it's been a while since he's been here. He got his undergraduate degree from the National Taiwan University, and then he got his PhD at Stanford. So that makes us sort of brothers, long distance. He was Steve's student. He also had a postdoc there and at Innsbruck. And he's been in Chicago since 2005. He's had lots of visiting positions, and I'm not going to go through all of them. And he's got several awards, including a career award. Let me get down to Sloan and a Packard Fellowship. So he's actually kind of smart. And a bunch of other distinguished awards. Now he works in AMO and atoms and molecules, and he's going to tell us a little bit about that here, a reaction of what he calls super quantum chemistry. And so we're looking forward to that. He also does some other stuff. We had a great talk this morning. So let's let him tell you what he's going to do. Thank you.
Can you hear me?
Sounds good on Zoom.
Oh, okay. I see. Okay, good. The only for remote. All right, it's great to be here. Okay, see a lot of old friends. Okay, that we know for decades, multiple decades. Bill, Paul, and Charles, Steve, and so on. Many of them. Okay, also new friends and so on. So I'm happy to tell you about our recent work. Okay, and this window say, and thanks for the invitation, and that this I've been here a couple of times. I remember last time I was talking about something totally different. Okay, I think you're more about this. Last time probably more about the BEC in the critical behavior in the critical regimes. Okay, but today I'm trying to show you this very recent work just in the past year and a half. Okay, try to move to the state field co-molecules and see this hopefully understand new type of kind of reactions in the quantum gases, atoms, and molecules. Okay, so try to get used to this. All right, so here's the Chicago downtown, and this our university is about kind of a 15-minute driving distance. Okay, and downtown is next to Michigan Lake. Okay. And this from the James Franck Institute, Enrico Fermi Institute, Department of Physics, that's supported by OSR at the moment, NSF, and also from the university. So I'll be focusing on this our experiment, this related to molecular BEC and the kind of many body reactions. Okay, but also just in this slide, I'll quickly go through some of the other efforts that we've been working in the past kind of a few years. Okay. Including quantum simulation of some of the interesting two or three body bound states in nuclear physics, trying to simulate some of the kind of models in cosmology, say earlier Keyboard Zurich kind of scaling. Okay, we tried a system called the critical point, or inflation, or more recently unroot radiation. Okay, and also in condensate model, that's certainly with a condensate. Yeah, it's a lot of interesting models that can be investigated. Our recent work related to RKKY physics. That's how impurity are talking to each other in the presence of the Fermi sea, and phonos in the Fermi gas, and the topological defects in the kind of synthetic field, as well as the more recent one, bilayer lattice in the bilayer optical lattices. Go back. All right, and then also about 3-4 years ago, we started looking into a new set of quantum dynamics, how we call Bose-Einstein works. If we try the system, try the nonlinearity of this BEC hard enough, you can see this kind of jets coming out, okay, coming out of the BEC, and that can be linked to the kind of jet structure people study particle physics and the pattern formation, okay, and this as well as high harmonic generation people study nonlinear optics. But today I'll be more focused on this recent work related to this chemistry going from atom to molecules, and ask what are the new guiding principles we can identify in the quantum degeneracy regime. I'll start with kind of some basic idea how we kind of induce a pairing. What are the new type of molecules that chemists typically don't really think about? Okay, but now it's accessible to us because we can work with in the ultracold regions. These include the Feshbach and the ephemeral molecules. And second, the main part will be under this formation, how to get this molecule to condense. Okay, and when you start with a condensate of atoms and create condensate of molecules, and the reaction, okay, how that the reaction different from the reaction you see in daily life. So a short introduction on this why we're excited about cold molecules. Okay, certainly we have been working with the atom for a longer time. We know how to do this cooling, okay, and we know how to get them cold enough to form a quantum degenerate gas. Trying to do the same thing on molecule is much harder. Many people are still trying, okay, different methods, okay, to get to lower temperature, okay, and to go to let me see, okay, go to lower temperature. Say on the horizontal axis, 0 is a Kelvin, mini Kelvin, micro Kelvin, and nano Kelvin. Vertically is a density, 1,000 atoms, 1,000 molecules per cubic centimeter. Medium atoms, medium atom, tritium atoms. When you go to lower temperature and higher density, okay, ultimately we'll be able to enter this quantum degeneracy region. That means all the particles go to the same quantum state, both in the internal degrees of freedom and external degrees of freedom. Okay, and this has been a kind of holy grail in this in the community, trying to condense molecules or form a degenerate Fermi gas or fermionic molecules. Okay, with a kind of potential kind of application on the horizon, okay, to control chemical reactions, do some kind of a quantum sensing metrology with higher sensitivity, and just the molecule additional degrees of freedom, okay, also for quantum engineering and this metrology, and also just to see more fundamentally, okay, how would the chemistry look like, okay, in the degeneracy region. So let me start with this figure, which is linked to this our collaboration with Paul Julian, like when I was a student, like over 25, I want to say 30, 25 years ago, yeah. Okay, so I was a student, like many of you in the audience, okay, that play with these atoms. Our original idea trying to study electric dipole moment electron, and I was working with Steve Chu, but somehow just go into opposite regime. We go to prepare a sample that's actually very, very dense. So we load it into the dipole trap and do some cooling, and then the density become very high. And I remember the first time I tried to look at the stability of this cesium atoms in the dipole trap. Okay, well I took a scan over I think about 100 gauss and so on. Okay, and most of the time the system pretty well behaved, happy. Okay, and this high density cesium cells seem to be stable, except I remember except for one single point, and that single point happened to just sitting on top of one of these resonance. Okay, and then by repeat experiment, there's only one single point that the entire condensate disappeared. Okay, I was very curious, and I tried to take a more careful, detailed scan. It's still only that single point, and they're always reproducible. Okay. Now I had to increase I still improve the resolution by almost a factor 100 to get a very detailed scan down to a few milligauss, and then eventually I got this. By the time I graduated, I was able to get a very, very kind of detailed scan and found that there are a few resonances up to about 150 gauss, and they are extremely narrow. They're about a few milligauss in width. Okay. And I believe the first model from Paul and also from Iter, there's no resonance in this range. Okay, but this is not a spatial resonance. So we are lost. Or what are these things? Okay, many years later, we can confirm this indeed are so-called Feshbach resonance, but belong to a special type of Feshbach resonance. Okay, which I'll explain in a moment. But first, what's a Feshbach resonance? Is are the entry point to molecules. Okay, what happens is when this you consider two particles separated by r. Okay, that's the horizontal axis here. Okay, I need to get used to this. All right, so this and then the particle can interact with some kind of potential. The potential between two particles is called the molecular potential. Okay, and typically attractive at long range and it become a repulsive at short range. So I mean, it can support bound state and this energy in the y direction. Okay, but these atoms are not really simple atom. The atom also has spin structure. They have electron spin, nuclear spin, and so on. So we can also prepare atom with a different spin configuration. They can collide like this. They will collide like this. When the atoms are prepared in different kind of what we call the spin channels, okay, then the collision can be a lot more interesting. For instance, consider the blue line. You can see two particles coming in. Okay, then they can energetically couple to a bound state that's supported by a different channel. Okay, the different channel just refers to this two atoms approaching each other with a different spin configuration. Okay, then you can use a magnetic field to adjust the energy between the two spin channels, and then the incident state, the blue arrows, can line up with the bound state supported by the upper channel, also called closed channel, right? And this leads to this resonant behavior, and also allow us to couple atoms, free atoms, to bound state. And bound state of two atoms is a molecular state. Okay. So it turns out what we saw in this earlier experiment is this comes from the fact that when you change the magnetic field, line up the energies together and lead to this resonance. Okay, and this resonance lead to the so-called the change of the scatteriness. Okay, you can modify the atomic interaction, make it repulsive attractive. But we can also see the molecules in the early experiment. What we do is that we apply additional laser. That laser can be tuned to some kind of molecular transition. Okay, and this laser will do nothing to the atoms. Okay, but they only excite molecules. Okay, so all the narrow resonance shows the system, the molecule has been built up in the system. And then we can use turn on the light, we can destroy the molecule, but not the atoms. Okay, all right. And a few years later, okay, finally in the experiment, in the lab, people can really see these molecules. Okay, so in order to see them, okay, in this experiment, you can see that this we apply the magnetic field. Okay, because didn't mention. So on the one on the left, okay, the original this cesium BEC, okay, about 60,000 cesium atoms. Okay. And then the first step, we bring the atom into the resonance and transfer population to molecular state. To really see them, so we apply a magnetic field gradient. Okay, and this atom molecule different magnetic moments, so it can be spatially separated when you apply the gradient for a few milliseconds. Okay, and then to image the molecules, what we realize is that we can also dissociate the molecule back to atoms, but they already been spatially separated, so dissociation will allow us to see where molecules are. Okay, the same idea was actually was the first kind of realized by this Cindy Rigo and David Jin. Okay, but at Gila and many groups follow up in this next couple of years. People use a similar kind of technique and create these molecules, optimize the transfer efficiency, and try to see whether this molecule remain kind of a molecular quantum gas. Okay. A second type of kind of molecule that people have studied near the resonance, in addition to the two-body resonance, these are bosons. So nothing prevents them from this talking to each other in the three-body sector. Okay, that this predictions coming from, this also in pretty early on in 1999. That's about a year that we saw that this two-body resonance is in cesium. Okay, and these two gentlemen with also with this James Burke. Okay, they proposed the idea that you can also see three-body bound states. Okay, in the same way that three particles come together. Okay, then there's a three-body process that can also lead to this formation of three-body bound states. The three-body triatomic molecules. And then in addition to that, there's also prediction for any kind of Feshbach resonance, assuming this origin. If you shift the Feshbach resonance to the center, okay, at the center is a two-body, there's a Feshbach resonance center. Then there will be a set of three-body bound states. And this is very universal. It's applied to any bosonic particles at low temperatures, okay, with a short-range interaction as a fusion into add. Okay, short-range interaction, bosonic systems, and then the low temperature, when they scatter, okay, near any two-body bound state, there will be a set of three-body bound states. Okay, and this prediction from origin from Efimov in nuclear physics. Okay, and now get a lot of excitement in our community. And the prediction is the following. Whenever you see any three-body bound states near the Feshbach resonance, you are supposed to see a series of them. They will follow this geometric scaling. What that means is the first state has the size of 1. The second state will have a size of lambda. And the next one will have a size of lambda squared, geometric scaling. So that means when you get closer and closer to the Feshbach resonance, scattering and diverges, in principle, you will see many three-body bound states. Okay, if you can go to 0 temperature, ideally you'll see infinite number of bound states. Okay. All right, and for the next couple of years, we've been looking into such kind of this evidence of this three-body bound states. And in 2006, we saw the first one, and then this couple of years later, based on a combination of lithium and cesium, we're able to show that near a Feshbach resonance right here. Okay, this is the resonance position in the lithium cesium system. And then you see this additional structure I will label B1, B2. It is another one. B3 disappeared, but you can see there's a small peak right here. And then you can also see just the three-body bound state kind of deviate from the two-body bound state with a magnetic field separation of 5 Gauss, 1 Gauss, and 0.2 Gauss. Indeed, they follow this geometric scaling with scaling factor of 5. Okay, so this will show that this ephemeral this Feshbach resonance allow us to create a two-body, but also allow us to kind of look at collision of 3 particles. But one thing is that this experiment is done based on thermal gas. Okay, so totally like to understand better about this reaction going from atom to molecules. How would that be different in the quantum regime? Right. So let me mention this slide. Okay, I think after all this work had kind of get a community excited. However, this you see. There are one group of people going for ground state molecules with ideas that in principle ground state molecules should be more stable. Okay, and like probably higher chance to get a BEC. Okay, and also ground state molecules are short range molecules that likely have this large in the case of kind of mixtures, say lithium cesium or rubidium potassium and so on. You should have a larger dipolar interaction. Okay, and maybe they are more chemically interesting. But today I'd like to show our work on this Feshbach molecule. These are very weakly bound molecules. Okay, and then in principle, they are such a long range molecule. People think this they're highly excited. They should be less stable. Okay, and also they are so long range, so the actual dipole moment is very weak because the electron electron from both atoms are independent. Okay, they don't form a kind of dipole moment. And people think they are probably chemical and uninteresting and no dipole moment.
The Feshbach molecule.
Yes.
You know, based on this diagram, is this like a vibronic or vibrationally excited state?
Yes. Okay.
Trap them in and then. Okay.
Yes, indeed. Okay, so because you need to line out the energy of the scattering atom to the molecular state, so these molecules are highly excited.
But
Okay.
is there also there's something to do with the spin as well? You said.
Yes, you need to have a different spin channel. If a scalar, as far as I know, if you have only kind of scalar atoms, like there will be no Feshbach resonance. Okay. All right. Okay. So quickly forward to the kind of past couple years. Now, say one one kind of milestone was realized from this JQI group at Gila. They start with rubidium potassium atoms. Indeed, they can create this fermionic molecule with a temperature below the Fermi temperature. So this is degenerate Fermi gas or molecules. Okay, yeah, this is great. And this molecule in the ground state. Okay, and while we have been kind of fully involved with other things, but this kind of 2 or 3 years ago, we started to come back to the molecules and try to see whether we can also get these molecules in our system, the cesium-2 molecule, to condense. Okay, and this is our recent work. We show that we can also kind of just condense these cesium-2 molecules. Okay, efficiency not great. Okay, however, I will show you this our evidence this molecule in this forms of condensate.
How many cesium-2 molecules are in those?
Right. So typically with atom, we're about 10 to 5. Okay. Yeah. And then for molecule, that would be Well, it's a 10, 15, 20%, so it's only few 10, 10 to 4. But you divide by 2 again, the 2 atom forms 1 molecule.
Now, the more the donut? Yeah, the color thing is yeah.
Yes, I will mention that in a moment. Okay. All right. So these molecules, this one specific, there are a couple molecular state we tried, but eventually with this molecule, this particular molecular state simply more stable, allow us to get a condensate here. So what we do is that we create a BEC around 25 Gauss or 23 Gauss, and then we can change the magnetic field, okay, and follow this path and convert about 10, 15%. And why we can only convert 10, 15%, I think later I can tell you why we couldn't get 100%. All right, and then we have spent some effort trying to characterize this molecular states. Okay, right. So from this diagram, you can see this the molecule of energy only on the order of few megahertz. Okay, so they're very, very highly excited. Okay, and this is very far away from the ground state. All right, and we can measure the molecular binding energy, and this how you see this kilohertz scale. Okay, we also characterize this molecule as so-called G-wave molecule. What this means is that these molecules are spinning. Okay, they're 4 units angular momentum. Okay.
Is this always the last bound state?
Yeah, the moment you create it, it will be the last bound state. But of course, when you go further down, then this other state becomes the last bound state. Yeah. Okay. Right. But also these are last bound state that can couple to the atomic continuum.
Right, then you
yes.
form other states if you
yes.
go closer to the resonance.
Yes. Sure. Okay. And the reason this molecule seem to be this stable is unknown. Okay. Right. We are still trying to figure this out. But here I can show the experimental data. This is earlier experiment when I was still a postdoc. These are more recent experiment. Okay. So there are not too many data point, but you can see there's simply overall trend. Earlier experiment was based on essentially kind of thermal gas or molecules. We can only get to about 250 nanokelvin. A few years later, this by Rudy group get down to 15 nano, and now we can get down to about 11 nanokelvin. And the expectation is that based on the threshold behavior, the colder you go, in principle, near the resonance, you can get larger cross section. Okay, and the larger cross section likely also means there's a faster kind of inelastic collision, inelastic loss, because inelastic cross section should also scale up. So this is the expectation. System in principle should become less stable. Okay. However, what we see is that the loss rate seems to follow this overall trend. You seem to be getting more and more stable. In our more recent experiment, the loss rate has down to 10 to minus 11 and eventually down to 10 to minus 12. If we also, this horizontal axis is how well we confine them into 2D. Okay, so, oh, sorry. Okay. All right, so when we get to the 2D regime, we see an additional kind of suppression. Now we're down to about 2 or 3 times 10 to minus 12. This, by the way, this loss rate is comparable to what KRB can reach. Okay, KRB in the ground state can reach. So in terms of collision stability, we are just as good as this fermionic molecule in the ground state. Okay, all right, and in addition to that, we can you can see our interaction time scale, which I'm going to show in a moment. Okay, this is higher than that, so that means the system is stable enough, okay, to form a kind of to see the many body interaction. Okay, and also factor 550 suppression from the theoretical the upper bound of this inelastic collision cross section. Okay. All right, so talking with Paul, we have some idea why this molecule could be stable, but the true calculation based on the molecular correlation between 2 molecules, especially the G-wave molecules, I think it's so very complicated. So far, just some idea. Perhaps the spinning molecule might have some dipole moment. So especially in 2D, there may be repulsive force that stabilize their collision. So this. Also working with Paul, now one student is now able to kind of do the calculation based on Paul's code. We're able to show the molecular wave function. Okay, so this is a molecule we created near this 19.8 Gauss. You see molecular wave function. There's a the inner classical turning point, outer classical turning point, roughly about kind of 4 nanometer. So these are reasonably small molecule, even though it's very highly excited. You can see there are many wiggles. That means it's highly excited. There's you can count the nodes and see what the vibrational quantum number. Okay, and so they are weakly bound, highly low vibrational excited molecules, and somehow they are reasonably stable. All right, so our experiment progress, the experiment procedure is the following. We start with a BEC, atomic BEC loaded into the box. Okay, it's a blue potential created by our digital micromirror device, something similar to what's inside the projector. Okay, you can project on the instead of project the pattern on the screen, we project the pattern onto the atoms and form a blue kind of box or circular box. Okay, so inside the box, the BEC has a uniform density. Okay, and in the third direction will compress it, so make a two-dimensional gas of atomic BEC. Atomic superfluid. Okay.
Well, I was just going to ask, so what exactly do you mean? Because in principle,
yes,
we're told
okay.
that 2D.
Yes, right. 2D. So we have finite size, your coherent length is comparable to the size of
so in
this.
other words, it's like a BKT.
Yes,
but
BKT,
deep
right.
enough that you can't tell the difference. From
that's right.
BEC.
Yeah, that's right. Good. No experts here. Okay. So the next step, we tune the magnetic field near the resonance, induce a resonant coupling from the atoms to the molecules. Okay. And to be careful, I draw this potential differently. You can see the molecular potential. I draw the blue line with a centrifugal repulsive barrier because this is a G-wave molecule. This is a 4 units angular momentum. That explains why the molecule has a smaller size. Okay, yeah, because they're confined within this small range. So the size given by the van der Waals length. After this coupling, now we need to blow atoms away. It turns out this when they are created, if you mix them together, we see a very fast loss. Okay, but as a pure molecule, they survive for a longer time. So immediately after the molecule created, within kind of less than a millisecond, we use a resonant light to blow the atoms away. Okay, and the molecule is insensitive to this light. All right, so this is in order to see the molecules. Okay, then once we blow away the atom, wait for some time, and then to see the molecule, we need to our here experiment, we still kind of dissociate molecule back to atoms. Okay, but if we do not dissociate, then you see nothing. The molecule is insensitive to light. To see the molecule, we dissociate them back to atoms. Okay, and this image, you can see these molecules that will stay inside the trap. All right, so the reason there is a hole in the middle, okay, it turns out our trap is not perfectly uniform. There's a weak anti-trap because we have a box. Okay, but we show the magnetic field. The magnetic field creates anti-trap. Okay, but anti-trap at the center is about 1 to 2 hertz higher than the potential outside. So it's tiny kind of anti-curvature. That anti-curvature is so small you do not see on the atoms. Okay, where atom is a much higher density, chemical potential much higher. But when you get to these molecules, the lower density, almost by factor 10, and chemical potential low enough to about only like kind of few 10, like 20, 30 hertz. So even a kind of 1, 2 hertz kind of anti-curvature, okay, will lead to this hole in the middle.
Now, are you in the Thomas Fermi limit, or
yes?
You're still
okay.
in the Thomas
Still
Fermi
in the Thomas Fermi limit.
That's
right, because you see such a tiny kind of potential shift. Okay. All right. So actually, that gives us an idea. So in order to, so how do you show this is a BEC? The conventional way can do time of flight, but these are very heavy. This is cesium-2. And the temperature later determines is a 10 or even a bit less than 10 nanokelvin. Expansion is super slow. Okay, right. So what we decided to do is that we saw this structure, and then that gave us an idea. We used a DMD to create a potential, okay, to introduce a potential at the center of the potential on the molecule, and see how the molecular density react or responds to the external potential we apply. Okay. So here's the result. So we change the essentially we change the chemical potential, okay, by using the additional light, okay, and see how much the density was reduced. From that, we can back out what is a kind of a density state. Go back to this. Okay. So, and we perform the same measurement on atomic BEC, make sure we know what we're doing. Okay, so we can see the density as a function of chemical potential. Okay, and if you reminded by in this classical thermodynamics. Okay, for a thermal gas, density chemical potential are linked by this exponential function. Okay, so increase the chemical potential, you will see the density will go up exponentially until the chemical potential reaches 0. Okay, in reality, in 2D gas need to be a bit higher than 0. But anyway, so chemical potential gets higher than 0, and then suddenly the system deviate from this exponential law and enter this superfluid regime where you expect a linear dependence between chemical potential and density, where the coefficient is given by the interaction strength. Okay, that mu equal to Gn. Okay, and that this coupling strength is characterized by the molecular scattering length. Okay. So perform this measurement, make sure we understand what we're doing with atoms, and then we do the same experiment on the molecules. Okay, and here in the y-axis is a phase space density. You can see our B's, we can get the molecular condensate is not great. The phase space density more around 10 and so on. Okay, but we enter the superfluid regime. Okay.
Now you've written, you said thermal gas, and then
Yes.
you said classical gas.
Yes.
You wrote classical thermal gas, but of course, as I get close to
Yes.
condensation,
Yes.
it's still thermal, but it's not classical.
Exactly.
What about that?
Okay. Yes. So that's something I don't plan to say, but you can see there's a green curve. Okay, that included this correction due to the non-classical properties
But it
of
doesn't follow.
interaction. Right. It doesn't follow. Somehow it follows much better with a thermal gas. Okay. So this is
Classical gas.
right. The classical gas. Okay. Classical gas, not thermal gas. Okay. Good. Okay.
So
I somehow this classical gas seems to provide a better fit, okay, to our data here. Okay, but I have to say when you get close to this zero scattering length, right, there is a deviation. It looks like it somehow follow this exponential curve much better. Okay, and before it switch to the linear curve. But I have to say around this region, we also don't have a great kind of theory model. Okay. Yeah.
I mean, would it make sense, like, so an exponential can be expanded in all powers of mu, right?
Yeah.
So then if it becomes linear at some point, would it make sense to think of like a lot of the coefficients except like the linear one having like mostly constant dependence, and then at some point they go to 0?
So you're asking whether it's possible this if you somehow think about the equation state as expansion, okay, and somehow all the higher order quadratic or the higher order term is suppressed to 0. Yeah, maybe that's an interesting way you can think about. Maybe you can expand it linearly with chemical potential. That's an interesting idea. Okay, I'm not sure whether it will work out, but I have to say this this formula is also not perfect. Because when you get close to the kind of in near the critical regime, you also have all kinds of this correction beyond this mean field result. Okay, so whether you can explain the entire phase transition based on the expansion, I'm not sure. Okay. All right. So in addition to this, that's what we reported, I think about a year and a half ago. Okay, and but more recently, we can directly just create a molecule also in harmonic molecular condensate, also a harmonic trap, so you can see the bimodal distribution directly. Okay. All right. So to conclude, we are able to create this molecule. They seem to be condensed. They follow kind of a generic kind of this bimodal distribution harmonic trap, or in a uniform trap, we can characterize based from this equation of state. Equation of state, that's right. And then we can see roughly 30%, the maximum probably to 50% kind of molecular condensate fraction. Okay, in the box.
What is that?
I'm going to talk about that's the dynamics. Okay, right. That's a very good question, because we always think if you start with the ground state of atom in the ground state, you can do some kind of say adiabatic transfer. You can go to the ground state when you change Hamiltonian to the new one. Okay. All right. The theory prediction is that the transition is not that easy. it's not a crossover, it's not like the BEC, BCS crossover, but there will be a phase transition in the middle. Okay, so this is an earlier kind of calculation, I think, from this Romans and also this is Subir such depth. Okay, essentially that based on is a kind of a mean field type of model based on this Hamiltonian like this. Okay, the first term is energy of the molecule. Second term is the coupling between atom molecule. Okay, and people think, well, okay, the Feshbach resonance, sure, you can write down that this the dynamics as two atoms being annihilated and one molecule being created, and the reverse process molecule dissociate back to two atoms. I think I'm just always pressing the wrong button. Okay, all right, and in the mean field, okay, then this is kind of the phase diagram, okay, and horizontally this is energy of the molecules. When the molecular energy is much higher, then you expect all the population go to the atomic state, okay. But when the molecular energy is lower, then you expect the ground state should be just a pure molecular condensate. So these are the two limits, okay. Now, vertical direction of the temperature, you can see, well, there is a, when atomic BEC being heated up, eventually will go back to the normal gas. Okay, so this is a critical TC. And so we normalize the temperature to the critical superfluid critical temperature for the atoms. So that's why this is 1. But we get to the molecules, here in this model, there's no loss. Okay, so 2 atoms will be converted into one molecule. Mass is twice as large, but number is halved. So therefore, the critical temperature much lower. Okay, so one idea is that we cannot get really very kind of a high BEC fraction in the molecular state, is that we had to have a very low temperature to begin with. Okay, it's just tough. The critical temperature for the molecule is almost factor 3 lower. Okay, but second, more interestingly, there is a prediction. There is, you see this line. I think there's a different calculation, but both of them suggest there's some kind of a some kind of phase transition. On one side, this is more atomic BEC, but the other side is molecular BEC, and then there should be a quantum phase transition.
So is there a regime of coexistence of an atomic BEC?
Yeah. So here, so that's a very good point. Around here, there will be some kind of a mixture. The wave function will be the atom mixed with the molecules. Okay, right. However, once you pass this point, then no atom will exist. Okay, they only have pure molecules. Okay, so here, but there's a right. Okay, that's a prediction. Okay. All right, and that diagram, this miss 1 line, which I add kind of based on our own calculation. That is, if you go to this high temperature, okay, I draw this dashed line. It's not a true phase transition, but that's just even for the normal atom, it can be converted into normal molecules. Okay, and this is not surprising. This is what we see in daily life. Okay, it can be driven by the interaction, can also be driven by temperature. So if you cool down the system, you can also cool atom and down to molecule because they can, yeah, when the molecular states have lower energy. Okay. So in principle, this would be what we consider kind of a thermal chemistry, is driven by thermal fluctuation and so on. However, the transition from here to there, from atomic BEC to molecular BEC, will be new. Okay. This will be collective behavior. All the atom molecule occupy the same state in the 2D physics, so we can set aside. Okay, so now whether this reaction in the many body regime will have show some new guiding principle for the quantum chemistry. Okay, that's something that kind of intrigues us. Okay,
But you expect it to be a phase transition rather than a crossover.
Yes.
The way it is.
that's right. According to the prediction, yeah. Yes.
So the previous transition between BEC and BEC is so that transition line divided by no atom, right?
Like here will be no atom. That's right.
No, I mean the super chemistry one. Because
Yeah.
you mentioned there could be some mixture between molecule and the atom on the other side. So to me, it's not clear to me either that's what should I think of this the transition or crossover? Because I could imagine, and I'm just curious if there is a regime that there's no molecule. on the
Right.
atom.
Right.
Or like in that region, you will
Right.
have like some continuous tuning.
Right. I can tell you experimentally, this difference very, very tiny. Our experiment mostly that far away on one side or far away on the other side. So what I'm going to, at least within what so far what we studied is what happens if you bring the system from atomic BEC quickly to the other side, and how does how do molecules how are molecules created? Okay.
I'm still, maybe it's a similar question, but I'm
Okay.
still confused. If I look at the phase transition line between
Yes.
molecular BEC and
Yeah.
atomic BEC.
Yes.
I mean, it's the line, if I'm going, say, toward lower molecular energy,
Yes.
is when I first start to see a molecular condensate,
Yes.
right? Now, let's say that I'm in the upper right-hand corner of the molecular condensate.
Upper right hand corner. You mean here?
No, but of the molecular BEC.
Yes.
So down there, but now I want to go up, but
Yes.
not to the line,
Yes.
below the line, and all the way to the right.
Yeah, I mean going like this.
No, right here. I want to be right here.
Oh, here.
Okay, now when I go lower in temperature, it
Yes,
looks like I'm
yes,
going
yes.
from a
Molecular
molecular
BEC
BEC.
back to
Now,
atomic
that
BEC.
seems weird.
That is weird, right? There is this curve. Okay. Yeah. Going this way is reasonable. Going that way is very
So
strange.
how do
Yeah.
I understand that?
Okay. I'm not sure I can so far also this is a tiny energy scale for us. Yeah. Yeah, that would be really cool to see how it cool down and some molecule dissociate when you cool. Yeah. Yeah, this is I agree. Yeah. Yes, I'll keep that in mind. You'll ask this question some point we should come back to this. All right. Okay. All right, so now let me compare this reaction in the normal regime and the many body regime. Normal regime, I think that we learn in general chemistry. Say collision is how the reaction happens. First, you need a particle to collide. Okay, and the collision rate would depend on the cross section, the velocity, and the density of the particles. Say, consider kind of similar type of reaction. This atom can collide and form a molecule. But if you use the Hamiltonian, the people have proposed. Now we're talking about the dynamical process for this atom molecule in the quantum regime. You would think you would start with the interaction with, or I should say, reaction part. So you described by these two terms. One is that you eliminate two atoms and create molecules. Okay, and these are field operator because atom form a field, molecule also form a field. It's a matterwave field of that forms that constitute this the condensate. And G is the coupling constant. Okay. All right. So write it down, and this is a good exercise if you learn this quantum mechanics. So the second quantization form. Okay. So you can try to solve it with a few limited number of particles. You can do exact organization. Okay. But you can just try to say, experimentally, I want to see what we should expect from the atomic this atom number and molecule number. Where I can write down the Heisenberg equation to see what is the equational state for the molecular field and for the atomic field. Write down this equation, immediately recognize the thing about this some kind of differential equation is the nonlinear differential equation because of phi a square. Okay, also you have two operator on the right side. Okay. Right. So what this means is that this the reaction process, okay, the reaction rate, okay, can depend on the population in a kind of a non-trivial way. It's nonlinear, and and also is supposed it should be coherent. Okay. You can have a phi a, I'm drawing here, the atom occupy the same wave function, go to molecule occupy the same wave function, and you have you can synthesize molecules, or you can also kind of dissociate the molecule back to atoms. All right. So if you're not familiar with this equation, or this nonlinear, so on, it looks like a mess. But something we learn in classical mechanics can try to look at how the second energy integration form. Okay, the energy should be conserved. Okay, So if you try to raise this, try to do some algebra in the same way, trying to see what's the conserved quantity. And this is so to me a little bit surprised. What we obtain is not just based on the way, it's not based on the field equation, the field amplitude. I'm looking at the molecular number, which is 5m take a 5m. Okay, so you see this is essentially the rate. How fast the molecule number is changing with time. Okay, and then that square plus some kind of function. That function only depends on molecular number, becomes a constant. And this whole thing looks like some kind of energy conservation. You have something like a kinetic energy term and a potential energy term. So if we treat the molecular number as some kind of a coordinate, okay, yeah, some particle, and then how fast the particle is moving, determine the kinetic energy, and then that together with the potential energy. Now you see this is a trading between kinetic energy and potential energy. But I need to remind you, these are field operators. Okay, somehow our intuition based on kind of classical variable, okay, can lead to very different result. Okay.
Now, are you thinking of this as all happening at 0 temperature?
Yes.
Yeah.
Okay. It's just a model. Okay. Certainly, we have finite temperature. We have other more complicated process.
For that, it's 0 temperature.
Right. For this model, just try to see what are the new guiding principles. If you can do in the ideal
Right, so
situation.
there's never any thermal stuff coming into the chemistry. There's no idea of things being exothermic or endothermic.
Because at the moment, these are trying to consider near resonance.
Everything
Yes,
is
every
energy.
economy. Right. In the ideal situation, when the system only described by this Feshbach coupling term,
Yeah.
then what do we expect to see? Okay. Now, similarly, we can also write down something in terms of three-body process. Okay, but you'll get a kind of a three atoms come together and create a molecule with atom together. Okay, this three-body recombination. But you can also write down another reaction potential. Okay, so eventually with our equation, we have this. We can draw this line. You can derive this potential, which I'm going to call that is some kind of effective reaction potential for this many-body system. If we have 100% atom or 100% molecule, because now we are not consider the simple situation exactly on resonance. In principle, they should share the same energy. Okay, with this on resonance, and we can set the energy to be 0. Now, but with any other combinations, yeah, they can be 20%, 80%, and so on. Now you can with that equation, we can draw this line. This is that reaction potential I that derived based on this Heisenberg equation and so on. Okay, you can see that indeed there is some kind of this local minimum. Equilibrium can happen with a particular kind of a certain fraction, but the ground state typically is a pretty complicated kind of superposition, or you will say even entanglement, kind of entangled state. Okay, between the atomic field, molecular field. All right. In addition to that, your classical kind of intuition might break down if you just think about release a system here. It should collide, it could go down to the other side and come back and so on. Okay, but this is no longer just one single degree of freedom. These are two fields. Okay, there's all kind of superposition that can happen. So we try to do this exact organization and try to see what will happen based on Hamiltonian. I just show you just one single term that shows a coupling between the atom molecules. And start with 100% atom to begin with, because that's what our experiment started with. 100% atom, so 0 molecules. Now let's evolve the system in the time given by the time scale of the coupling constant. So you can see the molecule number goes up. But at some point when you almost reach the other side, then starting kind of branch out and form all kind of very complicated structure. And what this means is that the system quickly becomes a crazy superposition. Okay, starting from 100% atom, that's near the bottom, or 100% molecule, that's near the top. Okay, right. So if you evaluate the expectation value, that's what the Heisenberg equation in principle can tell us. Okay, then what you will get is something like a oscillation in the potential, but together pretty strong damping. Okay, right. So even though we do not assume any damping in the system, but the expectation values seem to just with all the nonlinearities seem to suggest Okay, if you just experiment, it looks like there's some kind of oscillation, but only oscillate for a couple of times, and then you'll kind of move toward some kind of equilibrium.
So I take it that those black wiggly arrows are the damping.
Yes,
You're-
yes,
you're
some kind of
looking at-
effective damping.
Yeah.
Yeah, but
And you're gonna tell us what that is?
I can only tell from the calculation is from theory paper earlier literature. It consider this effective damping likely due to this superposition entanglement. Okay, which doesn't really reverse. Okay, even though systems show a pure state, but just expectation value seem to show this kind of damp oscillation. Okay,
I'm not quite happy.
I'm also not quite happy, but right.
Long enough, you're gonna have a kind of lazy signal in terms of like your atom number and your molecule number.
Right, it could be a lot of fluctuation. So that is indeed the case. If you believe, if our system really described by exact organization, I'm not claiming that, but if this is the case, okay, you will see a huge fluctuation, right? You see the color shows the kind of the probability, okay. Essentially, it's in the beginning very well defined, but afterwards it'll be large.
Definitely zero molecules.
Right.
But over there, it's kind of hard. It's like
Right. Maybe finite particle number you will revive and so on. But here, I think we're seeing 1,000 particles is likely just remain pretty ugly like this for a while. Okay. So you can see in the beginning, very well defined 100%. So zero molecule begin with, they follow this line all the way to the other side. Somehow, when almost reaching the other side, is suddenly kind of branch out and it just become pretty messy. So any particular time here, you can see the probability almost everywhere from 100% atom to 100% molecules. Yes.
So can I think this as some quench dynamics? Because
Yes. Yes.
So
Yeah.
then, actually, I think there are some point model study about quench dynamics for similar system and actually showing this.
Okay. Good. Good. Now, one thing I'd like to see what would be the form of the effective damping. Okay, it's not totally clear from this calculation.
Also, they will go to another. They will oscillate and eventually saturate to another finite long-term value. And I'm not sure about this particular model, but
Okay.
I know there are some studies I can show.
Yeah. Okay. Good. This is what we see. Our experiment, we start with 100% atoms. So you can see this is how 100%. Okay, and this zero molecule to begin with. Okay, and then we bring the system to resonance. Okay, and we can now change the field, the response time about 15 microsecond. So quickly bring it to resonance. Okay, and then we'll wait for a certain amount of time, and then try to see how many molecules being created and how many atoms are left. So you can see somehow within about a few hundred microseconds, there's a fast drop of atoms, and then followed by something we don't know how to describe. And afterwards, okay, with some enough effort, we show that this indeed this is show this oscillation. Okay. All right. Similar molecules, her molecule number increases. Okay, and then you also show some oscillation. Okay. And the sum of the two, and I'm plotting 2 times molecule because dissociate 1 molecule back to 2 atoms. Okay. So the sum is not 100%, but when the first kind of 1-2 milliseconds, you also have a kind of 20-30% missing. But most of the, yes.
Yeah.
Why does seem to be there's some phase?
Right, there seems to be some kind of phase shift. I'm not sure I have a good answer to you. Okay, if there's no loss, you would think they should be exactly out of phase, right? But in reality, I know it's not really out of phase. There's a phase shift also seems to depends on the condition. But because there's also missing fraction, I think there's a good reason to assume the missing fraction also somehow participate in a coherent way. And I think missing fraction probably also oscillates.
Okay, so
Okay.
what's the missing fraction besides atoms and molecules? What is there?
We maybe some deeply bound molecules that cannot be detected. Okay, right. But however, really deeply bound molecules likely will not contribute to the coherent evolution. So yeah. So, but this is all we can see. Yeah.
There's no loss as far as you can. in the sense of actual state.
There could be a scale. The typical molecule can scale because when they create but typical molecule typically coming from three-body process. When the molecule created, then the binding energy can be released.
I see.
Okay. Yeah. All right. So that first, I'll show you how I study on the first part. That so in the beginning, even though it might it looks like a linear as an experimentalist, to just try to determine what is the kind of this initial react kind of a rate from the atoms and try to fit this with a straight line. The first 100 microseconds and so on. This plot particularly is a look at this the atom loss rate. So in the first hundreds of microseconds, how fast the atom number is dropping. Okay. So as a function of magnetic field, so I shift the main Feshbach resonance to 0 here. And I need to 0 here. And the width of the resonance is 8.3 milligauss. Okay, this scale is a 0.0083. Okay, 8.3 milligauss. Okay. Then you say, well, 8.3 milligauss, so why do we scan over such a large range? Because somehow, even we're far away from the resonance, we can still see the lifetime start to be limited. Okay. All right. So here we're about 10-second lifetime. When you are 800 milligauss away from the resonance, then we go to 1 second, 100 microsecond, 100 millisecond, all the way to the top, only about 10 microseconds. Okay. The enormously enhance of this enhancement of the loss by many order of magnitude when you get closer and closer to resonance. But if you only look at the ring, then it looks like Lorentzian. Okay. The Lorentzian ring is symmetric on both sides. Because the Lorentzian and the symmetric, that seems to suggest likely in the winds is more like kind of two-body kind of type of resonance, kind of Feshbach coupling. Okay.
Cheng,
Yes.
we know that three-body loss scales is 8 to the 4th. That
Yes.
Ring tracing 8. Does that have anything to do with how it changes
Yes.
from far wing to the center?
Yes. Okay. The three-body process that's we believe is kind of become dominating when really near the resonance. Okay. And so here, yeah. I think, but however, I think it's even more complicated. So first of all, this what Paul is talking about is that near the resonance, then people have shown that three-bodied process can be enhanced as 8 to the 4th. Okay, so if the three-body process scale is 8 to the 4th, it will be faster than this Lorentzian. Okay, all right. Lorentzian one way is 1 over you say proportion a squared. Okay, will be faster. Second, this near the resonance, but this with a condensate. Okay, what we see here is even faster than this recombination by the three-body process. Okay, what we see is that this when you get close to resonance, now at this on the negative side, this on positive side. Okay, we see this enhancement which is no longer symmetric. Okay, that is you can look at more closely in the inset. Okay. Now this is only within plus minus 200 milligauss. You see, in the beginning it followed a green line, but then it deviates and this and then it shoots up. Okay, it's higher than this low extrapolation of the Lorentzian by order magnitude. Sorry. Okay, order magnitude. And also somehow this enhancement is stronger on the negative side. On the positive side, it also deviates. Okay, on the positive side, actually, this if you try to fit the positive side with this dotted line, it's closer to the prediction from this three-body process. Positive side is three-body process, but negative side is if you we try to fit it, so this line shows that it scales 8 to almost at the 8th power or 9th power. It's really steep. Okay, it shoots up to the roof. So I'll show you the original data. So if you stay far away from the resonance, this is about a couple of second lifetime. Get closer, 700 milligauss away from the resonance, 170, 100 milligauss away from the resonance. More or less, it follows some kind of it looks like some kind of single exponential. Okay, down to 40, 70 milligauss. Get even closer, 30 milligauss away, 28, 20, eventually less than 10 milligauss away. The dynamics no longer like a single exponential. You can see what happened here. It quickly dropped. And then for the next couple milliseconds, it seems to be not changing that much. Okay, this 9 milliseconds is kind of, you see how fast it drops within kind of few tenths of microsecond, and then stop. Okay, you cannot fit this with kind of single exponential, but it looks like it's a two-step process. Okay, really fast in the beginning. This is very close to resonance already. Very fast in the beginning, and then in the next kind of few milliseconds seem to be stable. Okay, if you wait for a long enough time, eventually the three bodies those will sort of take everything away. Okay, but that's over kind of tens of millisecond scale. Okay, but within the first few milliseconds, now it seems to stand a kind of reason that we want to separate dynamic into the relaxation part. That we believe that what happened with the system quickly go down to the minimum. Okay, with some kind of equilibrium, and then stay there for a while. Okay, at least for a couple milliseconds, and then over this time range, it looks like there's no more dynamics. Okay, not too much. Maybe some oscillation, but here you just fill it with a straight line, and then you see pretty much consistent with a very little loss for the next few milliseconds.
Now,
All right.
Is the eventual loss, does it go off and then get lost, or does it very slowly go away?
Yeah, eventually it does go away in kind of a 20, 30 millisecond scale. Okay.
It's
Yeah.
not like there's some critical time at which it goes away, it just decays.
Right.
Very slow time.
Right. Afterwards, it looks like just slow decay. There's no more kind of no more steps. Okay, so this is the beginning behavior. Now let me move on to the later behavior of these oscillations. Okay, this oscillation, try to see what determines oscillation when it's on resonance. Okay, yeah, and this is all the data taken on resonance. Okay. And one thing that came to us is that if you prepare the system differently, with a different number of atoms in the BEC, we start to see oscillation at different frequencies. This data is tough because the amplitude is only like a few hundred atoms. Okay, right. So, but you can see, so the error bar is large and so on. But eventually, we're able to, my students spend time trying to do Fourier transform to the fit and so on to what is, if there is oscillation, what is the best frequency, okay, to model the system. Okay, this is the result. Overall, you can see that going from few thousand to few tens of thousand atoms. Okay. Beginning with a larger sample to begin with, we see a faster oscillation. Okay, and this compile all the data from about 5,000 atoms all the way to 40,000 atoms by changing the atom number, okay, by factor 8. Okay, and this is the measurement. The error bar is not small because her data is not, yeah, it's a lot of fluctuation. Yeah. All right. So in tempting, just to try to compare this the prediction from this our first choice, it is a Feshbach coming from Feshbach coupling, right? But this is a fit. The prediction is that you're going to scale with a particle number to a power 1/5. Okay, right. Obvious. This is what is a 1/5, and then we change a coefficient in the front in order to fit the data. And this is certainly not great. Okay. All right. So, by looking at data, just well, we don't know what to do. Okay, so this not a very good model. Okay, but then at some point we're kind of brave enough to do the kind of three-body calculation, also determine what is the oscillation frequency. Okay, when system reach some kind of equilibrium. So the three-body coupling model will assume this on resonance. We only in your model we only including this term. That is, we're losing 3 atoms and create 1 atom, 1 molecule. This leads to a much stronger dependence on the density. Okay, for a reason that's probably clear to you already, because there are 1, 2, 3, 4, 5. There are 5 field operators. When you have many particles to begin with, and start to see this oscillation and so on, the coherent coupling strength will scale with will scale with the particle number. And depending on how every field operator, okay, in the many body regime can be approximately by the square root of particle number in the system. Okay, say he'll be. So that's why you can see that this the reaction of this oscillation frequency, okay, seem to scale much stronger with a stronger dependence on the density on the particle number here. Okay, as compared to 2 body. Okay. right? So if you ignore the theory and just try to say let's assume there's also some kind of power law, then exponent will determine 0.7. Okay, that is a better compare better with the 3-body model than the 2-body. Okay, right. So how do I understand this particle number dependence? Essentially, we think about this coherent reaction rate, even though it's small, is somehow is faster for more particles. This is similar to kind of a lasing action. You have a stimulated process. The more particle, the more population you have in the mode, that will enhance this scattering into the same mode. Okay, and right here, atoms form a mode, and molecule form another mode, and they are just we're talking about coherent coupling between them. All right, so if you're happy with that, we can go back to the theory, try to see this starting with Hamiltonian. This time I put in the kind of molecular energy term. Okay, yeah, and then you can derive this 3-body potential. Okay, it looks like it's a very simple Hamiltonian, but this potential you can derive it rigorously is pretty ugly. Okay, but the ugly potential, we part it out, it actually looks nice again. So you can see this potential is 0 on one side, 0 on the other side, but then you have this kind of local minimum. Okay, this potential tells us what is the lowest possible energy you can have for different molecular fraction. Okay, all right, and the molecular fraction can go from 0 to 100%. Okay, and then the minimum also happens 1/5. So this leads us to understand, to believe probably what we are seeing is the relaxation of this atom molecule system to some kind of new equilibrium, and then in the minimum, this the molecule fraction 1/5, but you need to divide by another factor 2 because 2 atoms forms a molecule and so on. So this is pretty much close to this what we see. If you look at if you really compare the kind of molecular fraction, that is the ratio of the molecule divided by the total particle number in the atom molecule that we can see in our experiment. Okay, so this is one more, and we see the molecule increases, but the fraction, it may be some oscillation, but if you feed the constant line, we also get something very close to 0.5, close to 1/5. Okay. All right. So let us summarize. So this by looking at this how atom couple the molecules, now we can see the fast enhanced reaction and these oscillations in the scale with a particle number. Okay, in the interesting form. Okay, and so far our conclusion is that it looks like the 3-body coupling, 3-body model seem to fit better the data we see. Okay, so we have 2 evidence. One is the scaling reaction, coherent reaction rate, okay, on the particle number. Second, okay, equilibrium, the system will reach about 0.2. That's in good agreement with the theory. And then the last line is what we're working on. Okay, according to either of this model, when you create atoms, you create molecules from atoms and so on, you lose two atoms and create 1 molecule. In principle, we should also see the phase doubling. Okay, and now we're currently working on try to see whether some kind of interfering experiment we can show that the phase of molecule should be 2 times the phase of the atom. Okay, I'm happy to discuss with you if any good idea how to really do this. Okay, all right. So that's pretty much everything I want to say about the molecule project. I'd like to thank my group members, in particular my former student Zheng Zhang. He did most of the work on the molecular condensate, and our current student Su Nagata, and also a new student, sorry, not included here, Jay Jatinowski. They are working on the testing the phase, okay, and also more about reaction rate. Okay. There are also other group member. I just show the kind of 2 slides, okay, on our lithium cesium experiment, okay, where we try to load BEC into a Fermi gas, okay, try to study the so-called how the phonon coming from the BEC can interact with a fermion through this kind of 1 loop, okay, and this interaction, okay, this is in the weak and the strong coupling regime. and see the phonon propagation with a different lithium Fermi, boson Fermi interaction. Lastly, when a new system just getting online, trying to look at individual particles, okay, in the lattice, and want to be able to use a tweezer to rearrange the particle in the system. All right, I'll come back to the conclusion here, and thank you for attention.
Thank you very much. I forgot to mention, Cheng's going to be available for the students and postdocs at 4 o'clock in the usual place. So please don't forget that. We are kind of late. Time for one question, other than Bill. One burning question.
So I'm thinking of like the textbook, mini particle Hamiltonian, where you write down some of your single particle operators and like your kinetic energy, and some maybe potential, and then your sum of your interaction, Bij, sum over all the pairs. But that just seems like that's just, I guess, an approximation here. That, you know, where does this E3 fit in? And why don't we normally talk about it? Why, you know, why?
Yes, if you consider this atom molecule, they all occupy different modes. Okay, their interaction will be independent. Okay. But now, since they're all in the same mode, okay, so essentially the reaction of this, you always need to symmetrize the wave function for the atom molecules. Okay, and that lead to this both enhancement, okay, of the coupling. Okay, another example, think about this atom coupled with a electromagnetic field. Okay, we know the field is a square root, but this is just tell you how many photons you have. Okay, and then the coupling also scale as a square root of particle for her photon number. That's the electric field. So you no longer treat atom photon in independent kind of coupling.
Let's thank.
All right, thank you.